If you want your system to scale, it needs to be a distributed system, spanning multiple computers and therefore able to handle a cornucopia of failures. This is Data Skeptic Consensus, the 10th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I speak to Heidi Howard about Paxos, a class of algorithms designed to help a network of machines replicate a shared state, also known as distributed consensus. Paxos is widely used and certainly impacts every listener on a daily basis through the systems and services we consume.
My name is Heidi Howard. I am a research fellow in computer science at Trinity Hall College at the University of Cambridge.
And can you tell me a little bit about your background?
So I do research into distributed systems. Specifically, I look at how we can build distributed systems that provide strong guarantees to their users, such as strong consistency guarantees, whilst making weak assumptions about the underlying system. I did my PhD recently. I finished in 2019, and my topic was distributed consensus, so very relevant for your series. Specifically, I looked at how we can build consensus algorithms that don't require majority agreement.
Awesome. Yeah. So far on our series about consensus, I've obviously covered it from many angles, not yet from the distributed systems point of view. So maybe could you help frame for some of the listeners what is challenging about managing consensus in computers? Don't I control all the software? Shouldn't this be easy?
You may write the software, but you do not control the software. And I think as anyone who's used a computer knows, you rarely control the computer either. Computers fail. It's not a matter of if they'll fail, or it's a matter of when they fail, to be honest. And when we're talking about distributed systems, we're not just talking about one computer or 10 computers. We're talking hundreds, thousands, tens of thousands of computers. Failures are no longer the exception. They're in fact the rule. They're an everyday occurrence. And this is why distributed consensus is so important and yet so difficult. So distributed consensus in the context of distributed systems is the problem of how we decide a value or a series of values between a set of servers, despite the fact that these servers might fail, that they might be slow, that they're going to communicate by messages that may or may not be delivered, and that they have clocks that we can't trust to even accurately tell us the time. So it's a really difficult problem to solve, but such an important and powerful primitive if we can get it right.
And I know the term NoSQL. I'm sure you have some relationship to that. Could you comment on it and maybe frame how this sort of umbrella of NoSQL solutions relate to distributed solutions and these types of algorithms?
So I am not really a databases person, so I don't know a whole lot about SQL versus NoSQL, to be honest with you. I work at a kind of a different level. So for me, database is just a box. Like we have many boxes, they're just applications. And what I look at is how we can give these applications the information and the kind of basic primitives that they need in order to do the stuff that they do, which is then to provide databases that might be SQL or NoSQL.
Gotcha, yeah. Well, let me ask you what I think is going to be a difficult question, given what I know about it. What is Paxos?
That is a difficult question, but fortunately I spent many years of my life banging my head against a wall thinking about this topic. So that is a nice question for me personally. So Paxos is an algorithm for solving the problem of distributed consensus. It was proposed by Turing Award winner Leslie Lamport in a paper which is titled Part-Time Parliament. It's quite a famous paper in computer science. It is very important and very hard to read. Parts of it are in Greek, like literally. It's a fun read, but it's a difficult read. And Paxos, despite the original presentation, it became very, very popular because it was the first and at the time the only widely known solution to distributed consensus. And obviously, Leslie Lamport is very famous and produces a lot of very good stuff as well. So when Leslie steps up and says, this is how you solve a problem, then, you listen and this is how you're going to solve that problem. And so Paxos became really widely used, and we see it used in systems by all the major companies. We see it used within Microsoft, we see it used within Google, we see it used within Twitter and Facebook, etc. So most distributed systems use Paxos in one form or another in order to solve distributed consensus.
And if we were to celebrate Paxos, what are some of the guarantees and things I get if I adopt it?
So what Paxos gives you is safety. Specifically, what it says is if you decide a value using Paxos, then that decision is final. If you decide a value with Paxos and you learn what that value is, then you have definitely learned the same value as everyone else in the system. Paxos is an algorithm that does not compromise. It will give you the right answer, and if it can't give you the right answer, it won't give you an answer. It will never ever compromise on consistency. So we can use this to build really strong consistency guarantees. So the strongest guarantee that we can have on a single object is called linearizability, and Paxos can give us linearizability.
And then I think many people, or at least I certainly see them come up together, will know Raft in contrast to Paxos, which I guess is really core to the thesis of the paper I asked you on to discuss, Paxos versus Raft. Have we reached consensus on distributed consensus? So maybe I can ask you the perhaps slightly easier question, what is Raft?
So Raft is an algorithm that was proposed, well, it was published in 2014, but it was proposed a couple of years before that. And the Raft paper was written in response to this issue with how we actually understand Paxos. So the Raft paper aims to write an algorithm for consensus that is as understandable as possible. So the paper is written in plain English, unlike the Greek of the original Paxos paper. In fact, the Raft paper was the first paper in consensus that I read, and I really liked it, and I implemented the algorithm, as did many other people. And then I thought, this is great. I want to do a PhD in this space. So even though I mostly work on Paxos nowadays, I actually wouldn't have even done my PhD in distributed consensus if it hadn't been for the Raft paper.
Oh, very cool.
Yeah. It's always kind of these two big armies competing against each other, the Paxos camp and the Raft camp. And people always assume, oh, I'm in the Paxos camp and I must hate Raft. And I'm like, no, if it wasn't for Raft, I wouldn't have even done my PhD. So it's very important to me personally as an algorithm. So the paper was really successful. So it was first put online in 2012. And before it was even published, there was already like 100 implementations of it because it was such an understandable paper, and engineers seemed to really enjoy and really resonate with the paper and wanted, once they read it, to actually implement it because they understood it, unlike the Paxos paper.
Wow. So is there a way we can track how much that impacted usage? I know some of these like NPM or pip will show you downloadability and stuff like that. Do you have any sense of vote by popularity, I guess, for these two approaches?
Yeah, so if you have a look on GitHub, I searched for Paxos and I got around 1,000 repositories that put Paxos in the README. I searched for Raft and I got around 5,000. So given that Raft is only a few years old and Paxos has been around for so long, that's really quite an incredible difference between the two.
Definitely. So ability to implement, that's obviously a win for Raft. Are there any other wins? Any reasons people would prefer it beyond that? Maybe something, in terms of its big O analysis or something like that?
Yeah, so both the algorithms are pretty similar in the way that they approach the problem of distributed consensus. And this was what the paper that you referred to was trying to kind of explore and to try to clarify. The big gain in Raft is the way that it does leadership election. So one of the core problems in consensus is deciding a leader in the system. And specifically, when we're deciding a leader, we need to ensure that whoever is in charge of the system knows about everything that happened in the system before they became the leader.
Well, why do we need a leader?
We don't necessarily need a leader. You can solve consensus without a leader. And that's something I'm actually just doing some work in right now. But a leader makes things so much easier. If you pick one server and say, you're in charge, you're the boss, you're going to decide what's going to happen, you're going to propose values, you're going to handle failures. It is so much simpler than if we let everybody propose values. So it's a little bit like giving a talk. If one person is clearly speaking to a room, that's a lot easier to manage than if everybody is trying to talk at the same time, because they end up colliding and no one gets heard, and then they retry and they might collide again. So having a leader just makes solving the problem of consensus a lot easier.
Gotcha, but in a truly distributed system, we have to account for the fact that our leader could disappear or stop being the leader, I suppose. How do we find a new one when that becomes necessary?
Absolutely. So everyone who's not the leader, their primary job is to keep an eye on the leader and make sure that the leader is still up and still there and doing what they should do. And so the leader's going to regularly send a heartbeat out to all the other servers to say, I'm still here, don't go replacing me just yet. But at some point, as you said, the leader will fail, and other servers are going to try and step up and they're going to try to become leaders. These servers are known as candidates, and they're going to run an election to try to become the leader. And it's during this election process that Raft and Paxos differ. So both algorithms ensure that a newly elected leader will know about all decisions taken by previous leaders. But the two algorithms differ slightly in how they actually ensure that property. So in Paxos, anybody can become leader. Any of the servers can be a new leader. And during the leadership election process, they learn about things that were decided in the past so that they don't contradict those decisions. Whereas in Paxos, we say you can only become a leader if you're already up to date. So the way that we implement this is when you're becoming a leader, you need votes from a majority of servers, and a server will only vote for you if you are more up to date or as up to date as it is. So that when a server becomes a leader, we know that it's at least as up to date as a majority of the other servers.
Gotcha. And do these two protocols have to account for anything security-oriented when that election takes place? Could there be a malicious member of the distributed fleet?
So that is a super interesting area. So this is known as Byzantine fault tolerance. And this is when we're dealing with the fact that servers, as well as being slow and stopping, they might just do basically anything. They might act arbitrarily. They might not follow the algorithm. They might skip steps. They might execute them out of order. They might be hacked. They might be trying to take over the system. And there's a whole separate family of algorithms that solves this. The big famous algorithm in Byzantine consensus is known as PBFT, which stands for Practical Byzantine Fault Tolerance. So Paxos and Raft don't handle this, but they have equivalents in this kind of parallel universe where we can't trust servers.
And I'm curious about the election process. You know, I've been a developer working on, let's say, a traditional ACID-compliant database and have gotten to situations where someone locked another table and I was kind of aware of it. If an election took place, would I, as a user of the system, experience any kind of delay while that happens?
So you may experience a little bit of a delay. It shouldn't be too much. Often consensus is not put in the kind of critical path of a system. We don't tend to put it right kind of where users are submitting requests and they're going through the system. We don't tend to put consensus there because consensus is a really expensive thing to implement. When you have consensus, whenever you want to make any decision, any change, you need to get a majority agreement. So you need to get a majority of servers to agree. And that is really, really expensive. If you want to do anything and you had to get a majority of people to agree, it would take a really long time. So instead, consensus is traditionally used for kind of configuring of distributed systems. So it's not used directly by users, but it's used by distributed systems to manage things like group membership and leadership election and who is a member of this system right now. So it's not generally put right kind of at the surface of systems where it will actually interfere with users.
Thanks to this week's sponsor, Monday.com. That's the site where over 100,000 teams rely on Monday.com for their daily work. If your team's not already using it, you should check it out and form an opinion about it. Most of you already know about Monday.com and their Work OS, but I want to make sure you've heard about the Monday Apps Challenge. That's right, Monday.com's Work OS is being extended. They're now opening up their apps framework, which helps developers create custom blocks. Set aside all the prizes. One of the things I really like about this challenge is it's practical. I know listeners out there, maybe a group of 2 or 3 of you, you could put your heads together and come up with something cool. Or maybe one of you's at a startup and you want to impress your boss by building out an integration between whatever the heck your SaaS solution does and Monday.com's platform. If your app can help even a few of those 100,000 teams using Monday.com, hey, that's a cool bonus. That's what this challenge is all about. Whether it's to help with marketing, construction, sales, software development, or anything in between, the challenge is looking for impactful, out-of-box, and simply amazing apps that can be introduced to their upcoming marketplace. This is the ground floor, a great entrepreneurial, pioneering opportunity. Learn more at monday.com/dataskeptic. Once more, that's monday.com/dataskeptic. Let's maybe talk about a worst case scenario where a leader goes offline and then during an election, the presumed winner goes offline before it becomes the leader. And then, just a bunch of crazy scenarios could have happen in some sort of all worst things at once. How will these protocols pan out in those types of situations?
So it varies on how the protocols are implemented. But what does unify all these protocols is that they do guarantee that once the network and servers stabilize, so once we have a situation where a majority of servers are up and they're able to communicate, then the system will quickly come back to a state where it is live and it's able to make decisions again. So anything can happen. We can go through great chaos and instability, but as soon as we're back in a universe where at least a majority are up, we'll be able to converge and make progress very quickly.
Very neat. So it sounds like it's extremely robust in that regard. What sort of use cases does that make these types of approaches best suited for?
So this is really useful when we're trying to configure and manage distributed systems. So if, for example, you're using containers, you might be using Kubernetes, which is some software that manages containers. Kubernetes uses a distributed key value store, which is called etcd, and etcd is built on the Raft algorithm. And so Kubernetes is able to store some state about the containers that it's managing in the etcd key value store. And that's a very classic example of how we use distributed consensus.
And you'd mentioned your introduction to this was through Raft, and Raft is the most popular one out there, at least by GitHub metrics. Yet, if I understood correctly, you said you spend most of your time working on Paxos. What puts you in that minority group?
Part of what makes Paxos more difficult to understand is that the algorithm is more general. So whilst if you've got a specific problem that you're trying to solve, if Raft fits that problem, then you're better off just using Raft. But because I'm interested in all sorts of distributed systems, I'm interested in strange distributed systems, I'm interested in distributed systems of the future where what was previously a bottleneck is now not a bottleneck, or where we're working on distributed systems at a global scale, for example, I really want that flexibility that you can get more easily with Paxos than you can with Raft. And so that's why I usually write my algorithms in Paxos kind of terminology. However, as we described in the paper, Paxos and Raft are so similar that you can translate optimizations and research from one algorithm to the other and back again. So it's not just useful for, if you do something in Paxos, it's not just useful for Paxos. If you do something with Raft, it's not just useful for Raft. Like, these two communities do not need to be distinct. We can share these optimizations across these two algorithms quite easily.
In terms of research direction, what are some of the next places you're exploring taking these things? It's a published algorithm, there's implementations. What's out there that's left to solve?
There's a lot left to solve, unfortunately for me. So one thing that I'm working on, and I actually just got the paper accepted today, so it's available on arXiv now, but the official version will be available in about a month or so. It's called Fast Flexible Paxos. So we discussed earlier about the fact that we have a leader, and what about in a distributed system? Can you have algorithms that don't have leaders? So Fast Paxos is an algorithm that solves consensus without using a leader. So it allows any of the servers to basically propose values to be decided without routing them all via a centralized leader. This is a really powerful way of designing algorithms, particularly if you want to operate them across data centers on a global scale. You don't have that extra latency of going all the way to a leader and back every time you want to get something done. But designing these algorithms is quite tricky. So the two big problems you have are collisions. So when, like in the big room, when you've got multiple people talking at the same time, if you don't have a leader, then you don't have control over who's going to be proposing values, so you've got to deal with collisions. And we need more than majority of servers to agree when we're making a decision. So with Paxos and with Raft, we're able to use majorities, and that's because any two majorities will overlap by at least one server. But when we don't have a leader, we need bigger groups. Typically around 2/3 of the servers need to be involved. And so the work that I've done recently is reducing that group size, and that work is called Fast Flexible Paxos, because I've done similar work in my PhD on Paxos, and that was called Flexible Paxos. So Fast Flexible Paxos is the speed of Fast Paxos combined with the flexibility of Fast Paxos.
Oh, very neat. That cross-data center or cross-region option is very relevant, I think, in today's cloud world. I'm curious about the structure of how you add an enhancement like that. I mean, is there a cost to be paid for having a leaderless system, or is there a hierarchy across the data centers? What's the basic abstraction?
So the basic abstraction is that any server can go ahead and propose a value. And if there was no conflicting proposals, then it's as if that server was the leader at that time. So basically, when you don't have too many values being proposed in different areas at the same time, this ends up working really, really efficiently. The problem is, and the price of these algorithms is that if you have really high load in lots of different places at the same time, that you get too many of these collisions that you have to deal with. And each time you have to handle a collision, it's a reasonably expensive operation.
And from a developer's point of view, I mean, obviously developers do many things, from front-end developers to distributed algorithm developers, but taking someone who's not as focused or as knowledgeable in your area, how much knowledge do you think they should have and appreciate for what goes on under the hood? Certainly, we need to know something about it, or are the problems so well solved that people can just trust the abstraction and they don't even need to worry about the fact that consistency and the cap theorem, all that stuff is somehow being managed under the hood?
I think it's really important to understand, at least at a high level, what's going on, because ultimately when failures occur, we need to know whether the system should be available or if the system will not be available in that scenario. So for example, if you're managing a system that's running Raft and it's using majorities, then you know that if one server fails, your system should actually still be up and should still be working. And if it's not, then something's awry. But if two servers go down, well, then you know that Raft wouldn't be able to cope with that. And so your system is going to be offline. So in order to kind of manage these systems, I think it is really useful to know, at least at a high level, what's going on with them. And something like the Raft paper or Paxos Made Simple paper is a good kind of high level introduction to these algorithms.
Do you have a sense of what sort of overhead or cost comes online with managing these? Obviously, the systems are trying to sync on some core data set, but they need to do the operation of the voting and all that kind of stuff. How much of my electric bill is going to that versus other things?
I think because they're generally not used in the critical path of applications, I don't think it's too much. Also, these algorithms do not scale. So if you have 3 servers running, say, Raft, and then you add 2 more servers, so you have 5 servers, the performance gets worse. If you add more and more servers, the performance gets much worse. The best performing number of servers for a consensus algorithm is 1. So you don't tend to run consensus algorithms across that many machines. You tend to keep them limited to a fairly small number, and therefore the bill is usually reasonably small.
Gotcha. So what's that asymptote look like? How big can a cluster in theory be if I really need to scale this up as big as I can?
Well, most papers talking about, and blog posts and things talking about production implementations, they usually talk about 3 servers. They occasionally talk about 5 servers. If you're really pushing it, 7 servers. But really, you don't want to be going beyond that, because every extra server or pair of servers, because we want to be using majorities, so pairs are a sensible choice. Every extra pair is just putting so much more load on that already really congested leader that it's really a big performance penalty for quite a small gain in fault tolerance.
I'm curious if you have advice for people first getting into the field. I guess it would naturally follow to maybe start with Raft, but is it worth the intellectual exercise to develop an appreciation for the less intuitive abstractions of Paxos? Do you gain a broader wisdom the way some people say linear algebra kind of does that for them?
Yeah, I think it is a really valuable exercise. There is a paper called Paxos Made Moderately Complex, which I would highly recommend, and it does basically exactly what it says on the tin. It explains Paxos. It does it in a way that is clear in Paxos terms, but doesn't gloss over the details. It really does go through all the details of Paxos, and it talks about various variants of Paxos that aren't discussed in something like the Raft paper. So I think that's a really nice starting point for kind of developing this intuition and learning about the algorithm without getting too deep into unnecessary theory.
We should probably touch on the cap theorem, which I think I referenced in passing. Consistency, availability, and partition tolerant, if I'm not mistaken. Could you frame Paxos amongst those 3 key properties?
Yeah, absolutely. So the mentality of Paxos, Raft, and all the consensus algorithms is never compromise on consistency. I will give you a consistent answer, and if I can't, I won't give you an answer. So what I will compromise on is availability. So I may not be able to always give you an answer. And I actually think that's quite a nice abstraction, because if that isn't good enough for your application, you can put a cache in front of it, which will always give you an answer and might give you an inconsistent answer. So if you've got a really strong guarantee of consistency, you can always make it weaker, but it's much harder to go the opposite way. And in terms of partition tolerance, if you've got a majority, then you're good to go. If you don't have a majority, then you're not going to have availability.
So it seems like a very reasonable and sensible way to deal with the CAP theorem and its sort of impossibility constraint. Are there any, industries or use cases that makes these approaches especially good or bad for?
So I think Paxos is really good when consistency is very, very critical to your application, where an inconsistency will lead to someone's pager going off in the middle of the night and them having to come into an office. So that's why we see Paxos and Raft and algorithm and other consensus algorithms. They're used in things like Zookeeper, in things like etcd and Kubernetes and other such systems. They're bad for applications where availability is important. And particularly applications where consistency isn't that important. If we were having an instant messaging chat, that is not a good use case for consensus because we really want that availability. I want to receive the messages. In fact, it doesn't necessarily always matter that they're in perfect order. I just really want to receive them. So if availability is really important to your application, then consensus is not the answer.
So if you want to study these sorts of things, as you do, and maybe some listeners may aspire to, naturally there's some computer science here. Are there any other fields that are important, maybe aspects of mathematics that help in the understanding or the exploration of these ideas?
Yeah, mathematics is definitely important, particularly set theory. So a lot of the work I've done in the past and on my PhD was on what's known as quorum systems. So this is how we can guarantee intersection between any two groups without just using majorities. And the whole field of quorum systems is incredibly interesting and super useful for computer science, but is pretty heavily mathematical. And I definitely had to pull out some textbooks before I was able to do the work that I needed to do. So yeah, definitely some mathematics there.
Fun stuff. Heidi, where can people follow you online?
Mostly you can find me on Twitter. My handle is @HeidiAnn360.
Excellent. We'll have a link to that in the show notes. Thank you so much for taking the time to come on and share your expertise.
Thank you so much for having me. I love to talk about consensus.
That concludes this installment of Data Skeptic Consensus. Our guest today was Heidi Howard. Our theme song is Paradox by Oddly. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.